During this section of notes, we're going to talk about a couple of things. And those things are thinking like a scientist and doing science. And all that means is that we simply evaluate evidence. So, to get started, we're going to start with how we study the natural world. Now, the main thing here is to remember that we are limited by our senses. What we can see, hear, smell, and touch. You'll have to pardon my nose and my hand, but you get the point. We are only limited to what we can perceive. If we can't perceive it, we can't study it. Now, we do extend our senses with technology, things like telescopes and microscopes. We successfully do this with three basic assumptions. And these three assumptions are what allow every single scientist in every single field, discipline, whatever, to actually determine what's going on and what might be causing what we observe and how we can modify what we see to produce a particular change. So the first thing is this idea of cause and effect. And we're kind of already aware of this a little bit because we talk about cause and effect all the time. The second thing is universal perception. This one's a little trickier because, as anyone knows, if you watch a cop show, eyewitnesses rarely see the same thing or have the same description of what happened. So this is why a lot of things are standardized in science, like we see with the metric system. It's an effort to make sure that everybody, no matter their location, knows and understands the meaning. This is also where you get standardization of language and why science has special terms for different things observed. And the last big assumption is the idea that the laws of nature are constant and universal. In other words, no matter what, if he lets go, that's going to fall because gravity is constant. All right, so how we achieve and pursue this is through the process of science, doing science. And when we do science, we do call it the scientific method. Now, the main thing to remember about the scientific method, and it is the most important thing to remember, it's nonlinear. That means it doesn't go in a straight line. It doesn't have A going to B, going to C, etc. In other words, it's continually built on itself. It may move in random directions. It may change and go unexpected places that we don't know or anticipate. The whole point of science is to understand the world better, to get that deeper understanding about what is going on. So the idea is to throw out that idea that the scientific method is a formula. In other words, it's different activities in different sequences at different times. It just goes and makes decisions are made based on the results. In other words, we can potentially change a conclusion if we get enough evidence to do so. The history of science is filled with instances like that. When we talk about plate tectonics, when we talk about the understanding of the atom, etc., it's always built on this idea that conclusions can change based on evidence. And last but not least, it requires a community, because everything that is studied through science and a conclusion that is drawn through science is shared. And it's shared for a couple of reasons. So that other people can see what we've discovered and maybe build on it, or so others can check our results, kind of like what happened with cold fusion a few years ago. Now, though we're talking about this as though it's a little different than what you've normally seen or probably typically seen, it still involves the same basic idea, which is this focus on testing ideas. So, to test an idea, you always make a hypothesis. And the whole point of a hypothesis is the idea that it is the cause and effect in the relationship. And what you want to recognize is what role the hypothesis is fulfilling in that cause and effect relationship. In other words, what is observed is the effect. What we see, something caused that. And so the hypotheses are the possible causes of what was observed. It's typically limited to specific situations, and it's limited to what we know before we actually run any experiment. Now, once you can test the explanation, which means the explanation has to be testable, I have to be able to make a prediction and say, okay, I expect this, let's look at the result. You have to figure out what's going on. You have to figure out if the explanation did if that really was the cause of what you observed. And the thing to remember as well is that we can never really prove with absolute certainty that this is the cause, because there's so many things involved in doing a science, so many things we can never really account for. Now, when we attempt to account for that cause and effect relationship, when we attempt to account for what happened here producing this result, that's the basics of an experiment. You guys have been doing this all your lives in some way or another, because ultimately, when you pause to look both ways before crossing the street, you're evaluating the evidence and whether it is safe to cross the street. And that's all that's going on in any experiment. Now, we structure it or organize it in a very specific way though, because we really want one of two outcomes in any experiment. We want to know whether the results support the hypothesis or whether they refute or show that it's wrong. And so that's really ultimately, was the explanation right? Now, to do that, then if it was right, that means you better have evidence. Now, if it was wrong, you better have evidence. Evidence is the kicker here. You have to have evidence or data to support whether the explanation worked or didn't. And the cool thing is, it's never really done. Even if you're able to say, okay, yes, this hypothesis explained this, there might be something else that leads to a new question. So it's never really done. Science keeps going. So to do science well, there are do's and don'ts, as with everything. The biggest idea is you don't manipulate your variables, because it may be physically impossible. You can't necessarily get into, and once you've started an experiment, and change what's going on. The other reason is it eliminates the idea of that cause and effect relationship that we're looking to observe, we're looking to see. Did dropping the marker let go, was gravity the cause, or was there something else going on? And if you have a lot of variables, you never really get this cause and this effect. You can never tie them together. And lastly, it's considered ethically unacceptable. In other words, it's like cheating. You just don't do it, because then your credibility's out the window, etc. Now, what you do is you have to recognize a couple of things. First, errors are uncertainties, but an uncertainty is not the same as an unknown. In other words, we may be able to run an experiment, and we've done this one experiment enough that we can say 95% of the time we're going to get this particular result. That 5% is an uncertainty in the data, but it's not an unknown. It's not like if I stick my hand in an empty box, I don't know what's in there. The second thing is you have to know the sources of error. So that would be just basic mistakes, human inexperience. In other words, when you first do a lab in here, you may be uncomfortable, or the equipment may be new. You may not do as well with it the first time as you will, say, the 5th time. Instrument limitations. So some balances, for example, will weigh to 1/10 of a gram, and some weigh to 1,000th of a gram. So the limitation in what you're using for mass or whatever can limit and introduce error. The very act of observing can sometimes introduce error. Let's say there are things going on within something you're observing that can lead to potential other causes and can open that up. There are certain things that are beyond your control. A lot of stuff that we talk about with nutrition, for example. We're doing our best to figure out a cause and effect relationship within the body, but there's so many other factors and things going on in the body that there's a lot of uncertainty about what's influencing the outcome. And then sampling. And this is actually, you see this a lot more in biology and other things where you need a large sample to really see what's going on. Think of it like flipping a coin. If you flip a coin once, you got a 50-50 chance. If you flip a quarter 2 or 3 times in a row, you may get heads every single time. So now you're going to say, okay, every time I flip a coin, I'm going to get heads. But if you did that 100 times or 1,000 times, you'd start getting something closer to 50%. So now we've talked about what the errors are and the sources of error. The idea is to reduce the impact of the error. Because really, if we reduce the impact of the error, we can have a little bit more certainty, a little more confidence about the cause and effect we were trying to investigate. But more importantly, you then have to be able to explain how that error could have impacted your results. So, for example, let's say instead of flipping quarters, we're flipping pennies. And I'm going to give you pennies in kind of a, we'll put them in one of those roasting pans. I'm going to put another roasting pan on top, and you're going to shake it back and forth, and then we're going to flip it over really quick and then remove that and see how the pennies came out. Are some heads up, are some tails up, etc. Now, if you shook this and some of the pennies flew out, well, that's going to affect the results here when you count how many became heads or how many became tails. So you just have to be able to explain how that error impacted your results. Well, losing pennies affected the number, or the potential number here, of what could have been heads or tails. So now what that brings us to is this idea of variables. Ultimately, in an experiment, we have to manipulate variables. And manipulating of variables is basically, that's our cause and effect. We control this process because we want to be able to see what's going to happen. Let me back up a step real quick. When we talk about controlled, we're controlling the variables. Now, our independent variable is typically what we think of as the manipulated variable. It's what we alter in an experiment. In other words, it's what we think the cause is of what we observed. The dependent variable is what's measured. It's the effect. So if my independent variable is the cause and my dependent variable is the effect, this is why when we talk about graphing and various things like that, we graph a particular way. And we'll deal with that next. But here's the kicker. If I want to control something then, if I want to control my variables, that's what allows me to reinforce, determine, have confidence about the cause and effect. And I control the experiment by making sure there are no other extra variables. I control the experiment by making sure I'm the one that's changing the independent variable. And if controlling all of that, I see or observe something else going on, then I know that something else could be affecting it, and it's not just what I'm manipulating and what I'm changing and what I'm altering. And that's simply the nature of being controlled. So ultimately, again, you had two goals through all of this. Thinking like a scientist and doing science, and basically being able to evaluate evidence.